Welcome everybody to AMS Weather Band's latest webinar, Eclipse 2023 to 2024, a different kind of sunblock, with Dr. Lika Guhathakurta, Dr. Janine Fisher, and Dave Jones. Now, before we begin today, of course, as always, I would like to address some of the guidelines for our webinars. First, if you do have any questions at all for our panelists or moderator, please put it in the Q&A box at the bottom of your Zoom screen. It's to the left of the chat. And then we will be looking at those for questions to address. We just want to make sure all the questions are in one spot. So please resist putting comments in there just so that we can keep everything organized. We will also have some specific time for questions from the audience at the end of the presentation, but they may also be addressed during the course of the presentation, depending upon the flow of things. Now I'd like to introduce you to today's moderator. Thank you, Janine, for joining us today. Dr. Janine Fisher is a program scientist in the NASA Heliophysicist Space Weather Program and a valued member of the AMS Weather Band Committee. Dr. Fisher's expertise and connections have been instrumental in organizing this webinar. So Dr. Fisher, the floor is yours.
Thanks, Gideon. Welcome, everyone, and I'm happy to introduce our presenters for today. First, we have Dave Jones. He's a weather industry veteran and the CEO of Storm Center Communications, Inc., which developed the GeoCollaborate technology. GeoCollaborate places all participants on the same map at the same time, improving situational awareness and decision-making across sectors, agencies, organizations. Jones is an SBA Tibbetts Award winner and a member of various organizations such as the NOAA Extreme Events Ocean Observing Task Team and co-chairs the ESIP Disasters Life Cycle and Wildfire Clusters. We also have with us Lika Guhathakurta, who has led the development of heliophysics as an integrated scientific discipline from which fundamental discoveries about our universe provide direct societal benefits. She made possible the flagship missions, for example, Solar Dynamics Observatory, Van Allen probes, Solar Orbiter Collaboration, and Parker Solar Probe, including stereo, that would revolutionize our understanding of how the sun shapes space weather in our solar system. Since 2017, she has been the driving force at NASA headquarters and at NASA Ames behind the growth of Frontier Development Laboratory, both in terms of the breadth of problem areas tackled, as well as in the number of agency and industry partners. She is presently a senior advisor for the new initiatives at Goddard Space Flight Center and a program scientist at NASA headquarters, Heliophysics. So ready to begin. So over to you, Dave.
Janine, thank you so much, and welcome to everybody who is joining us today. It's really very exciting to have Lika. We call her Dr. Lika. That's how you can put the questions in the Q&A here with us today, because in just 3 days, the country is going to experience an annular eclipse. Now, for those of you who aren't going to be under that path of annularity, it's going to be a partial solar eclipse. We're going to talk all about that. We'll talk about the eclipse coming next April as well, which has a lot of excitement with that. And we have a lot of pictures and things like that to show you. So thanks so much for joining us tonight. And we hope that those of you who have kids have gathered them around the computer and are putting this full screen, because I'll tell you, pictures of the sun are just incredible. And we're going to share some of those with you tonight. So, Lika, it's great to have you here. I'd love for you to get started. Lika has a presentation that she's going to share with us. And then while you're seeing Lika give the presentation about the sun, please think about questions and ask those questions in the Q&A at the bottom of your screen, and we will go through them and answer them, because we want to make sure that you are totally prepared for what's going to happen on Saturday and also what's coming up in April. So, Lika, thanks so much for joining us this evening, and I'd like you to start off with a few words and then dive into your presentation.
It's delightful to be here. You know, participating in events has become so much easier because we can do it online and we can go to places we need to go to. I mean, this wasn't quite the routine way of doing presentation for 2017. I tracked or flew to every meeting for those. So I am really happy to be here and, part of kind of this webinar is not only the beauty of Eclipse that we are all going to enjoy, but also sort of the things we do at NASA or the science that such events have made possible. So with that, if, I'm going to actually, for bandwidth issues from home, that's one of the downside. You really have to have fiber optics or something like that to really do this well when you want to see high quality movies. So I'm going to, my personal video, I'll mute it while I'm giving the talk so that I can save everything for the visuals I have for you. And I just wanted to know, do I share my screen now or am I already sharing my screen? I don't know.
Go ahead and share your screen, Lika. We don't see anything quite yet, but when you share it, I'll let you know that we can see it okay.
Okay.
Okay, we see your slide deck. So if you put that into presentation mode, we should be good to go. Beautiful. The floor is yours, or the space, we should say. And you're muted, Lika.
I'm sorry. So I said lots of things before that you didn't hear, maybe. Oh my God. That is kind of sad, but that's okay because I'll be talking for a while here. So yes, I'm starting off, with some very bold statements, right? I mean, I don't know how many of you in the audience know that we really live in the outer atmosphere of our magnetically variable star. I don't know. I can't see hands. Now, if this was a live audience, I'd challenge, like, who knew this before? And it is that outer atmosphere on the upper left-hand corner that you're looking at. It's the corona, the outer atmosphere. That's what you can see with unaided eyes, only during a total solar eclipse. Not even if the sun is 99.9% really covered. You just don't see the corona because it is so faint. And so, on the upper left-hand corner, that's our Earth. And anyone who has ever seen a picture of Earth that's been taken from deep space, generally will think of words like splendid isolation. And these are people, astronauts, who have actually shared their thoughts with us, just surrounded by millions of miles of really uninterrupted bear with me just a second because I want to stop my personal video. Okay, that's what. Can you still hear me?
We can hear you just fine, Lika.
Okay. And then so, often we have heard sort of stories that I need to go back to where I was, the very beginning. We have heard that people feel that our planet is really very alone, very disconnected. It just feels empty, and space is like that. And the reason I'm sharing this is because nothing could be further from the truth, because our planet Earth is actually profoundly connected to our star. And the bright blue disk that astronauts or people going into deep space see is just the most obvious evidence of that. And this beautiful picture of the eclipse that you see, the corona, It is that atmosphere that dynamically propagates into our planet, all other planets, into the heliosphere, into the edge of the interstellar medium. We can't see it as clearly, as beautifully, because it becomes very tenuous, but we are connected to our sun. So, it's almost, when I give you this talk, it's like I'm telling a story, and my story might sound like a cliche because it revolves around the sun. But I would say, isn't that true for all of us? I mean, what is a birthday after all? Another revolution of a person on planet Earth around the sun? And yes, it is my favorite star. I'll say it up front, and I'd like to ask you, isn't it yours? So the upper right-hand corner, what you see is actually the moon's shadows sweeping across the planet Earth from the vantage point of space. And if you have ever seen shadow approaching from Earth, it is absolutely incredible, even eerie and ominous. It is a very unique experience that you could have during the total solar eclipse in 8th April 2024. Over a period of less than an hour, it gets dark, the light gets very eerie, the colors change, and then abruptly it gets 10,000 times darker in the last minute. And that is what is overwhelming. That is what is fundamentally different from just having an ordinary sunset where the sun actually disappears versus the moon actually covering the bright disk of the sun. And this blocking of the sun, I love the title that Gideon gave, right? A different kind of sunblock. Yes, and this blocking of the sun during an eclipse has a huge effect because it reduces the sunlight, lots of different kinds of radiation, changes the temperature on the ground and air, and makes the ionosphere, and we'll come to that, it's the electrically charged layer just above our neutral atmosphere. It makes it less ionized. And these quick changing conditions can affect local weather, and that's why it is really very hard to predict conditions for a total solar eclipse. It changes ionospheric variability, animal behavior. People are studying actually behavior of, human beings like us, and host of other effects. And so I hope you take yourself to the total solar eclipse. Now, on the left side is the picture, and on the left side is actually, and I don't know why it's not playing. Let me play the movie. It actually gives you a modeled picture of the environment that we live in. So we have a magnetosphere, much like sun has a magnetic field, and you are seeing this magnetosphere being really pushed by the radiation pressure, the radiation energy, particle interaction, and it's almost like this cocoon that's quivering under whatever comes from the sun. And as I have written down here, we live under a sort of umbrella, which is our magnetic field, the magnetosphere. But unfortunately, the magnetosphere always isn't a reliable shield, and that leads to lots of, effects for space weather conditions. So, this whole field has sort of emerged as an integrated discipline only in the last 25 or so years. Heliophysics, which is this new branch of science, it's a new discipline. It's a made-up word, and it didn't exist before 2005. It is the physical domain defined by the sun, but it is not just the sun, not just solar physics. It's the domain defined by the sun, the heliosphere, just like astrophysics is the study of the physical domain defined by stars. And so this physical domain includes the sun itself, the solar system, everything inside the solar system, and stretches to the very edge of the interstellar medium. So in other words, heliophysics studies everything inside the sun's domain of influence. Just want to give you some samples of what is it we study, what is it we mean when we say we are looking at sun and its impact. We are looking at the sun as an astrophysical object. It's a star. It has all different layers. Thermonuclear fusion at the very core really generates the heat, and it takes a lot of time for that heat to propagate through the radiative zone, the convection zone, to chromosphere, photosphere, and then into corona, the surface. And there are all kinds of interesting features that we can observe because of the magnetic variability of our stars. So the things that varies as the sun goes through its cycle in life, and the bigger cycle is the 11-year cycle, solar max, solar mean, and we are in the phase of solar max nearly. So those variabilities are particles and magnetic field. Particles like electrons, protons, photons, which is radiation, like X-rays, like ultraviolet rays that energizes our atmosphere, like infrared rays, every spectrum that you can think of. And then there is solar wind. The sun is continuously losing particles in the form of solar wind, electrons, protons, and some other heavier ions. And all of this variability, all of these elements then come and impinge on our particular atmosphere. Now, remember this, every planet has its own environment. We are extremely lucky that we have a neutral atmosphere, that we have an ionosphere, plasmasphere, and the very end, we have a magnetosphere that protects us from some of these harmful conditions from the sun. And study of this interaction really is heliophysics. And it is not just sun-Earth, it's sun and other planets. And now we can study sun and other planets and use those models to even study exoplanets. So, so there are significant societal consequences of solar variability. Otherwise, we wouldn't be, expending so much resources between so many agencies to study heliophysics. And heliophysics impact is space weather. So just like we have meteorology, which is earth science, and its impact is terrestrial weather. Very similar, but fundamentally different in terms of physics. So, what are the consequences? We have a permanent presence of humans in Earth orbit, and eventually human voyages beyond Earth. That's kind of already beginning to happen. And so solar variability can affect human space flight, satellite operations, smart power grids, GPS navigation, emergency radio communications, air travel, financial services, and even terrestrial climate. A whole host of things that, the variable conditions on the sun can affect. Now, what I want to show you here is that it is not just Earth, but everything in the environment of solar system is affected by this variability. And at the bottom, so on the top, you see again sort of a model simulation of our magnetosphere. That's our cocoon, our umbrella protecting us. You already saw the upper right-hand picture of actual physical model, simulated numerical simulation with data. On the lower left-hand side is like amazing. This is Comet Encke. That was comet tail is disconnected, not by radiation pressure, but by magnetic reconnection. And we caught so many of these with stereo spacecraft. And on the lower right-hand corner, of course, the most obvious, beautiful manifestation of of a solar storm is aurora, and this is captured essentially from space station. And this is kind of a really good season to go catch auroras, both in the northern and southern magnetic latitude. I don't want to go too much into this, but what this is really, I showed you the variability aspect of sun. What is it that's varying, right? What is it we observe, we measure? So when there is an ultraviolet and X-ray radiation from a solar flare, that directly goes into our atmosphere and energizes the ionosphere. And all of these conditions are happening because our sun is actually a very ordinary star, but it's a magnetic variable star, and it's the magnetic field, essentially. Then we have things like charged particles. These are energized electrons, protons, and ions. And because they have mass, they move a little bit slower than the speed of light, and they affect all sorts of electronics in space. Sensitive electronics are turned off. If you have solar arrays, they can be affected, all of that. And then the thing that we learned sort of at the very end of our learning, as we kind of connected Sun, Earth as a system, are what's called coronal mass ejections. These are magnetized blobs of solar material that can travel, at its fastest speed, like within a day, but at slower speed, it takes about, between 2 to 4 days to come and impinge on our magnetosphere and squish it and generate electromagnetic fluctuations that drive current through the soil that can trip power grid at its extreme. It's possible. It has happened. So the effects of space weather is just really diverse. And it's never a quiet time for space weather. Whether it's solar maximum or whether it's solar minimum, there are different conditions that are in display. And these are basically, just a movie showing you some of the impacts of space weather, of solar variability. Basically anything with on-off electromagnetic switch or electrical switch can potentially malfunction. Especially vulnerable are power grids that I talked about as a result of coronal mass ejections. But it can be our satellites in space, or it can be our astronauts, doing extravehicular activity and getting extra dose of radiation. So we have to study the sun. We have to monitor the sun, as NOAA does, our sister agency. We have to do forecasting, for which we, NASA, generate the understanding, the knowledge. NOAA does the prediction. Now, it's as I mentioned, that it is not just our planet, right? It is every planet, everything in the solar system sort of responds to the varying conditions of the sun. So there are auroras in many places. You can see, for example, Jupiter, Saturn, and you can see the gorgeous kind of auroras right now taking place in our own environment, and the various ionization that leads to this process. Now, one thing to remember is that, we don't talk about it, but magnetic field may be the most important thing that protects us from the solar wind, and is that a condition for habitability? And this is, I'm going to show this kind of fast. This is a movie, again, generated from data at Mars. And what's this showing is that you can lose essentially lot of mass from the atmosphere of Mars, because Mars doesn't have a strong magnetic field like we do. They are losing something like 100 grams, per second. And so, right now, Mars is not habitable because it doesn't have the robust atmosphere that we have. So we don't know. This is an area of study where the magnetic field is a precondition for habitability. Just as Earth is protected from solar energetic particles by its magnetosphere, the solar system is protected from galactic cosmic rays, and these are essentially highly ionized nuclei that come from supernovae explosion and all that from interstellar medium. And our sun's magnetic field essentially creates the same kind of bubble around the solar system and protect us in the solar system. And so in ways, cosmic rays can be much harsher than solar flares that generate solar energetic particles. I'm not going to go into details, but I'm just kind of making you aware. Sun is a very dominant player, but cosmic rays coming from outside the solar system play a very significant role. And so let's talk about space weather. Basically, since I think we've been observing the sun with SOHO for over 25 years. We launched Solar Dynamics Observatory, and then we launched the 2 stereo probes that went away from the sun-Earth line. And this essentially gave us a 360 view of what the sun is doing. We could see the front side and the far side of the sun at the same time with the 2 stereo probe, essentially. And the data from SDO, SOHO, stereo allowed us to actually model space weather evolution, CME propagation, solar wind propagation, all the way to the edge of our solar system. And so space weather essentially was born when the 2 stereo spacecraft could give us a view, 360 view, both the far side of the sun and the front side of the sun. But it just doesn't end there. We have done so many cool things. The stereo spacecraft actually has 5 set of telescopes, and these are little strange geometry to show you essentially the sun-Earth distance, which is 93 million miles. So the 5 telescopes on stereo is actually capturing a solar storm with 2 different vantage points and generated stereoscopic image of a solar storm for the first time. It's never been done before. And this is something we have to continue to do because this is what is unleashed at us all the time. And if we can see the complexity of the storms, how fast they are moving, what the geometry of the magnetic field is, we can do better with prediction. And so it's not just our star, but the entire, our planet, but the entire solar system basically lives with this star. And this is, again, you're seeing the, the breadth of the observations that the stereo spacecraft have given us. This is the model I was talking about. So taking all of this data, we can now routinely do forecasting of what's going to happen at the very many spacecraft that NASA has, or, all our planets where we have lots of spacecraft. And so these tools are actually very important for doing launches, for figuring out when to launch something, lots of it. So the landscape is changed. And so basically where I want to take you here is that we sort of kind of grew from being a consuming science to a producing science. The consuming science is curiosity driven. A producing science is also kind of showing its benefit to societal relevance, very much like earth science, but we are talking of space science, right? So now we know space weather is no longer the domain of earth only. Space weather is now also interplanetary, as I was showing you all these aurora pictures, the magnetic field of other planets as depicted here, but space weather also became exoplanetary because people are now beginning to model essentially exoplanets that we are discovering in our Milky Way galaxy and elsewhere. You know, we can model those stars and we can model the condition of space weather experience by that exoplanet. And very often we find that it is not just water, that Goldilocks zone that we talk of, that is essential for habitability, but the condition of space weather really determines whether the planet will even have an atmosphere.
Lika, if I can interrupt you, we have a
Yes.
question I'd like to,
Yes.
to say. So what do you find most surprising about the sun?
That it still changes every day, that we can't predict it, no matter how much we observe it. The magnetic field of the sun, it's this, it's invisible, right? And we do not see it, we model it, but we are still not very good at predicting it. We can do nowcasting, but forecasting a solar flare becomes very, very difficult. And, these are some of the reasons we are flying the satellites we are flying. And one of the satellites is Parker Solar Probe, which is going to go within very, very close to the sun in the same environment as the corona that we see, and essentially measure what the sun is made up of in that environment to give us data that we can use as ground truth in our model. So how much time do I have? I need to speed up. Please.
Yeah, Lika, I think maybe about 10 more minutes so we can get to other questions and get into a conversation. So
Okay.
Looks like you're right about at the eclipse, which is a good timing.
Actually, hang on. I do want to show this because if I don't get to finish, at least you will hear this from my voice.
Has an opportunity to sort of transform us in a way, especially the younger generation who will re-experience it in America in 2024 in a very profound way. I mean, this eclipse has an opportunity to tell people that science works, the methods of science works. We can predict this event. We can predict future events. You can teach about basic geometry of what's happening during the eclipse. You can talk about our endeavor to find exoplanets, that the techniques we use in detecting exoplanets in far, far away solar system is nothing but, that particular moon in another solar system or a planet sort of casting a dip in the stellar brightness. So, if we can take people closer to that with real examples, I mean, what's better than?
So, this is kind of not to scale geometry of what happens during either a total solar eclipse or a partial eclipse or an annular eclipse, which is what is coming up on October 14th. The moon is perfectly aligned between sun and earth, and the umbra, that very dark region, and it moves, of course, that's what creates the shadow and that's what creates the path. That's where you're going to be able to see either the totality or the annularity, whatever the case may be. Now, there is a broader shadow, and that is the penumbra, and that's where you see essentially the partial eclipses. Now, what is the difference between annular and total solar eclipse? Annular eclipse is when the moon's shadow is actually smaller than the disk of the sun. So there is a little bit of ring chromosphere left around the sun. And so we don't achieve totality. And that happens. Why is the shadow smaller? It's because the moon is actually at its furthest point in its orbit. So this variation of the moon covering the surface of the sun can go anywhere from 7% undercover to 10% overcover, basically, because of the geometry of the system, because the sun and earth, they vary over time because nothing is moving around each other in a circle. They're all ellipses. They all have inclined orbits about which they revolve. So, and same thing, moon also has the same situation going on with Earth. And all of these conditions lead to the various kinds of variability of partial eclipses, total eclipses, and annular eclipses. And so this is the same thing. Kind of, you can, if you want, you can take pictures. Solarsystem.nasa.gov. Eclipses has incredible wealth. I would urge you to go there. This is our path of annularity. And again, there are incredible detailed picture. What you can see, this what we call circle or ellipses, they are neither circle nor ellipses, right? This shadow region in the path of annularity, they have edges to it. That's because we have been able to do the topography of the moon, I think, in terms of tens of meters resolution from LRO and other observation, which is giving us the exact, place where we are going to be able to observe either annularity or totality. And what's amazing is we are so fortunate. We have the annular eclipse happening on 14th of October, and then on 8th of April, we have the total solar eclipse. And the same thing, I would urge you to go to NASA website. There are incredible details and zooming in capability if you want to check out where you want to be. Now,
hey, Lika.
Yes.
I have one quick question for you.
Yes.
Where are you going to be during the annular eclipse?
So I am leaving tomorrow. I'm going to go to San Antonio, and I am going to be at Uvalde near Garner State Park. I will be at Garner State Park for this eclipse because I think the conditions are going to be just right. And I'll ask you a question later. So what you're seeing here, I'm showing you this picture from 2017 eclipse only because I want to show you something else for which I couldn't find an equivalent for 2024 generated yet. So take a look at this. This was the eclipse of 2017. And what I'm going to point out here is, the cutoff insolation. So what happens when the moon blocks the sun? It cuts off radiation, different kinds of radiation, and you can see the shadow gradually moving. And that, as I was telling you earlier, has lots of consequences, essentially, for our ionosphere, for our local climate, all of it. And this is safety first, really. I should have put this up first. So during an annular eclipse, it is never safe to look directly at the sun without specialized eye protection designed for solar viewing. And who better can demonstrate that? This is Dr. Nikki Fox, who is our Associate Administrator for Science. So please pay attention. Now, there are lots of different ways of observing the eclipse without wearing glasses. There are indirect ways. You can see how you can create kind of projection device by crossing your fingers. You can see the crescent shapes here. You can use colanders. There again, please go to the NASA website and you will find lots of different ways of actually observing the eclipse when you can only look at the sun through, viewing glasses appropriate for eclipse. Now we are doing, of course, signs during the annular eclipse. It is less in amount than what we would be doing during the total solar eclipse, because that's a phenomenal state where we get to study the inner region of the sun in kind of exquisite details that we can't do from any other way, from any other observing platform. But for annular eclipse, again, we can understand and determine the conditions that the ionosphere experiences, where we cut off that solar radiation, solar ultraviolet X-rays, as I was talking of. So there's a cool set of experiments that's happening. And in partnership with Embry-Riddle University, there are 3 rockets that are going to be launched, suborbital rockets, 35 minutes before peak eclipse, and then during peak eclipse, and then after peak eclipse. And this is basically to explore how the eclipse shadow promotes irregularities which affect, GPS, GNSS, navigation, and everything else. And we are going to be able to kind of provide some assessment on that.
Lika, another question for you. How often do we have an annular versus a total solar eclipse?
That's a good question. I don't know if there is I'm sure everything has a periodicity, and I don't know the periodicity. But there was an annular eclipse that was visible in 2012. I think that was from Antarctica, Australia, someplace like that. So it's a very good question. I'm sure there is some mathematical formulation to the various geometries that will kind of tell us exactly how often they happen. This will be my first annular eclipse. I haven't seen one. And if I'm lucky enough to see it without cloud, then that's what it will be.
Okay, great.
So,
just another follow-up. So is there any cycle to the eclipse locations and or path?
There are things called Saros cycle, and these cycles kind of happen about every 18 years and few months. And basically, the conditions of the alignment of the sun, moon, and earth are very similar during this Saros cycle. And but the path is not the same. So even though everything else about the nature of the eclipse in terms of the alignment is similar, the eclipses are typically moving the path of totality about 120 degrees west, based on, again, kind of how this whole Saros cycle works. So I will tell you a story maybe at the end about this. But yes, so 2024 eclipse is going to be a Saros cycle 139, I believe.
Okay,
yes.
Wonderful. And I'm just going to ask a quick question to Dave, because I want to make sure this might be on people's minds. Someone's asking, what's the predicted weather for Saturday's eclipse for people across the nation? Unless you want to talk about that later, Dave.
Yeah, let's let Lika get through.
Okay.
Lika, you have 2 minutes.
Okay. Oh my God. Okay.
The rest of your slides, and then we'll
no
get to
more,
this question.
No more science. That's what Dave is telling me. He wants to talk about weather, which is what will determine whether we view it or not. But there are lots of cool science we are doing, even during the annular eclipse. And then, of course, very important is this, we are doing all of this under the banner of Heliophysics Big Year. And Heliophysics Big Year basically connects the 2 eclipses and the closest approach of Parker Solar Probe, which is going to be December 24, 2024. So we have created really a lot of events, a lot of citizen science, a lot of public engagement to make people aware of heliophysics. These are our set of missions. If you ever want to look at it, you can go here, and this changes. Sometimes missions retire and new missions are born. We have, I think, about 19 operating spacecraft right now. And so the other very big event for the heliophysics big year, of course, is the sun itself. And sun presently is going through a phase called solar maximum. So in solar minimum, you can see it's less dynamic. During solar maximum, it's seething and bubbling a lot more and gives rise to more flares, more coronal mass ejections, and there are more space weather conditions that are reported and outages and all of that. So, it's bracketing two eclipses and the closest approach of Parker Solar Probe and Solar Max celebration, one way of looking at it. These are basically, lots of different kinds of citizen science under the shadow that NASA has apps, tools, and ways for you to participate if you want to. These are, again, kind of a bigger list of those citizen science projects. I urge you to actually go to NASA HEAT website and look this up. And this is really my last slide. And, this is from 2017. And at that time, in 2017 Eclipse, I wondered about what would be the biggest way of touching everyone with the message of Eclipse and for people to go out and view it and enjoy it. And I think, first ever thermochromic ink stamp comes close to that. And that is, I think, the Postmaster General. I got kind of a framed picture of that. That was a very, very cool moment. And I think we did raise a lot of awareness about our science and eclipses in general. Thank you.
Oh, Lika, that's terrific. We have some questions for you to ask. And I also wanted to share with some folks. I'm going to, as soon as you stop sharing your screen, I'll stop here and share a portion of mine. I just want, when you showed the colanders and how you can use those, this is not how you want to use the colanders, I would think. Is that right, Lika?
No, yes. Yeah, if you want to protect your head, it will scatter the light some.
Yes, exactly. Well, I just have to say that Lika and I were in Oregon for the eclipse in 2017, and it was just incredible. One of the things that we had was a whole stadium basically full of people. And they were asking questions. And look at this picture. Make sure that you heed what Lika said, and that is to wear eye protection whenever you're going to observe an eclipse. The only time you can take that protection off is during a total solar eclipse, when you're in the path of totality and the moon is covering the entire sun. And that's only for maybe a couple of minutes. Then you have to put that protection back on. But I will get to this one question about the weather forecast, and then we'll go turn back to Lika with the questions. So what is the forecast for this path of annularity? And so this is what we have. What's the best place to go see this eclipse? And it looks like, based on the latest computer forecast guidance, for you weather nerds out there, I'm looking at the GFS model, and you can see down here around San Antonio, Texas here, and all through southwestern Texas, these numbers in the sun are what's predicted at the time of the eclipse as far as cloud cover. So there's 15% of the sky may have clouds in it in Texas. That's good for eclipse viewing. And as you get further into Texas, look at this in Midland, Odessa, 16% of the sky being covered in clouds. So you have an awesome chance of seeing this annular eclipse. 25% of the sky in Roswell. It looks like Roswell, New Mexico might be a great place to go see the eclipse. Maybe you can dress up for Halloween there as well when you go. And Albuquerque, 48% of the sky at the time of the eclipse may have clouds in it. So there's a chance there could be some obscuration, but there could be a chance that there's none where the sun and the moon are lining up. And then as you get up towards Utah, Bryce Canyon, Utah, there's about almost a 50% sky predicted to be covered in clouds. So that means there's a 50% chance of you seeing the eclipse very clearly. But when you get up and towards Nevada, look at this, Winnemucca, Nevada, in northern Nevada. We're watching out for you there in Winnemucca. 53% of the sky will have clouds in it. The temperature will be 51 degrees. You can see the temperature at eclipse time for these different areas. So if you want warmth and clear skies, it's the Southwest right in here in New Mexico and Texas. And if you're headed up to Coos Bay, Oregon, I'm sorry. This was a question for Lika. You know, when there's an eclipse and it's cloudy and or raining, what do you do? What do you do when it's cloudy and you want to do something to help with the observing the eclipse?
Yeah, I want to give that answer. But before that, I want to tell the audience that, you know, it's really Earth that protects us from seeing the eclipse, right? Sun, moon, they're doing their job and Earth is creating cloud. So what do? You go fly a kite. And we literally did this because we've been to eclipses trying to observe the corona. And, you know, about, I'd say, 50% of them turn out to be cloudy. So I went to Antarctica, and this is where this question was raised. And we saw real darkness in Antarctica when we were expecting to see a total solar eclipse in December 2021. And the question was, can we fly a kite? This is the first demonstration of flying a kite and actually getting spectral measurements from about, you know, these kites can fly up to, I think, 4 kilometers. This didn't go as high. But, you know, and those clouds are very high up. But this was a demonstration that you can carry instruments on kites. And there'll be more kite flying, actually, in the upcoming eclipse.
Oh, that's great. That's great, Lika. I also, you know, I remember when we were in Salem, Oregon, one thing that really hit me, this particular picture is a camera is pointed up at the sun. This is during a total solar eclipse. Camera's pointed up at the sun. Look how little bit of the sun is showing through. This is about 98% coverage, but look how light it is still outside. So when you're thinking about going to the path of totality on April 8th of 2024, make sure you get in that path of totality, because 98%, 99% is not good enough. It's still quite bright because the sun is so powerful. This is how it looked with the naked eye. You could see up there the little black dot covering the sun. That is the sun, and you can see how much of the sun is shining through. Not too much. So it's very, very surprising. And, you know,
can I say something here?
Sure.
Actually,
yes.
That is not what you see through your naked eyes. That's what you see through your naked camera or iPhone
That's right.
filter. You know,
That's right.
eyes are amazing. Eyes have in itself radial gradient filter that, you know, in order to put it on telescope, we have to devise it. But when you see the eclipse with your unaided eyes, it is spectacular. It is somewhat analogous to the pictures that I was showing.
Yeah, you know, and the thing that really surprised me, Lika, when you mentioned the pinhole projectors and things, this was how it looked through the leaves of trees. This is a shadow. You can see the tree, that's the shadows, but where there are little openings in the leaves or between the leaves and branches, you see all these eclipses. It's like a bonus. You get
it's
all,
like a painting.
it's like a painting, and all these pictures. I told everybody, I said, look down, look at the shadows. People started gathering around, looking down at those shadows. And you know what? If you don't have a colander that you can take outside and let the sun shine through and then project what the eclipse looks like, I'm sure you probably have a Ritz cracker. And so if you have a cracker, saltines will work too. If you have that, it'll project right through and you'll see these little eclipses coming right through there. And so it's just phenomenal. So Lika, I just wanted to ask you, what can people do during the eclipse when it's coming up in 3 days? If they're going to be close to the path of annularity, what do you suggest that they do that day?
So for most people, unless you are actually performing scientific experiment, my advice is that just pay attention to the moment. You're going to see Bailey's beads actually during the annularity. There's a lot more anticipation for totality, but even for the annularity. And through the glasses, you are going to see a beautiful ring. If we are lucky, we might see some, filaments, these magnetic field lines. These are, it's kind of pinkish in color, this part of the outer atmosphere, because this is ionized hydrogen that is actually producing these structure. It's absolutely beautiful.
And you mentioned Bailey's beads. What can you explain to everybody what Bailey's beads are?
Yeah, Bailey's beads are essentially, when you have the first contact where the moon just makes contact with the sun, and then in the second contact, the other side of the moon makes contact inside the sun. And when that happens, basically, you have sunlight going through the valleys amongst the mountains on the moon. And that's what gives rise to this fabulous, bead-like structure. So that's the diamond ring. And the beads come before the diamond ring. Diamond ring is the last ray of sunlight going through the valley between mountains. But there's actually, I didn't mention, there is this citizen science experiment going on, and they are doing their practice for the annular eclipse to look at, with Android phone or iPhone, the Bailey's beads from different locations. Now, because we have GPS and we can really accurately tell where we are located and the timestamp, I think these measurements and the various Bailey's beads observed from different paths along the annularity is going to give people an ability to kind of establish the circumference of the sun. It's a science project, but it's also a citizen science contributed project, because we need lots of people with lots of data actually taking measurements.
Yeah, that's terrific. Janine? Yeah.
Yeah, I was gonna say, Dave, do we have time to squeeze in one more question?
We do, absolutely.
Okay. So so I think it's more towards Lika, but either of you can answer it. If kids or students want to get into heliophysics, what should they study in school?
Well, have to study math, have to study science when you get to high school, maybe physics, but science, math, physics in high school level is very, very important. Heliophysics is a little complicated amongst all the sciences, but it's a very broad science area. So there's a whole lot of things you can do in heliophysics. You can design instruments, you can be a space weather forecaster, you can actually, study the evolution of sunspots and active region. It's really, the variety is breathtaking. So just doing some basic reading, writing, arithmetic, like my parents used to say in my days, is probably the best way to get started and do some computer science.
Yeah, and Lika, as a follow-up, someone's asking, is there a specific major in college? And I know we've talked about this, right? You can't find a major in heliophysics.
There is no major in heliophysics, but you can do aeronomy, you can do ionospheric physics. Many colleges will offer solar physics, but there isn't any heliophysics. And I'm still trying. If you know of any colleges, let me know who will teach heliophysics as one subject.
Well, Lika, I also had a question. I know it's possible. I think we can go at least a couple of minutes off. I'm going to, or past 8 o'clock. I'm going to stop my screen sharing because I want to start up something else here, because I have a question for you about sunspots. Could you just describe what they are and why do we need to study them? What's important about sunspots?
So sunspots are these dark regions that we see on the sun. Sometimes they can be so big that we can actually see one with naked eyes. I mean, that's a big sunspot and we need to watch out. Now, why are sunspots dark? The sunspots are magnetically very, very intense. And the reason sunspots are dark, because the magnetic field is so much stronger than the neighboring region, that it really inhibits that heat conduction, heat coming out. And therefore, the neighboring regions are brighter, but the sunspots are darker. Now, because the magnetic field is so high and it can become very complex, these are regions that can actually give rise to a solar flare. A solar flare is probably one of the largest explosions in the solar system, and it can do a lot of bad things for us.
So when we're
we want
watching...
to study it to understand it, to see if we can understand it enough to predict it, otherwise monitor it, and then figure out almost as quickly as we can, what did it produce, how is it propagating, what kind of energy is it carrying, all of that. And all these various satellites that I showed you, we're trying to link all of this knowledge together.
Yeah, that's really incredible. And I just wanted to tell everybody that the images that you're seeing right now on your screen are live images of the sun. This is from NASA's Solar Dynamics Observatory. We're watching sunspots. NASA Space Science is studying these sunspots because, as Lika described, these sunspots, when they rotate around the sun and they're pointed at the Earth, we got to watch and pay attention to those closely, don't we, Lika?
We do.
I mean, if there's a coronal mass ejection coming out of a sunspot that's pointed towards the Earth, we could have some impacts, and
that could be a bad day for us, depending.
It could be a bad day. We think bad bandwidth on a Zoom is a bad day. Well, maybe not having any bandwidth or having GPS.
Oh, there'll be no, yes.
Yeah.
I mean, there'll be all sorts of effects like that.
Yeah. We don't want GPS to go out. That's for sure. So, okay. Well, that's great. I'm gonna stop sharing my screen there. This has been terrific. I see we do have a couple of other questions. I'm just going to ask Gideon with the AMS. Can we go a little bit long, or are we getting the hook?
Oh, you know what? For this one, just don't tell anybody. Go ahead.
Okay, this is great. So, Janine, do you want to ask the next question? I think there was a question there from a ham operator, I believe.
Oh, sure. I think this might have been a response. I think there was an original question, and then Lika, you answered it, and there's a follow-up. So
oh, gotcha. Okay.
I think this is the follow-up. But basically, someone had a question about the ionosphere and the impacts during the eclipse, and then they were mentioning they're involved with the HAMSCI project, and they're saying the focus is to introduce citizens to how solar dynamics influence our day-to-day lives. So
it's a really fun time, and HAMSCI operators are going to gather data for the annular eclipse. It doesn't matter, even partial annual, whenever you have cut off solar radiation, the ionosphere is going to respond. and kind of understanding that response function is really important. And yes, it's through radio waves that we communicate, and the ham sci operators just have a ball because all of a sudden you're talking to people that you had no chance before of talking because your radio waves actually went to a different area. So it changes, your density, atmospheric density changes, and the propagation changes as a consequence. It's really fun.
That is incredible. And I just wanted to share this too, because I have a lot going on here in the screen with regard to solar observing. And Lika mentioned SOHO. This actually image right here is monitoring of coronal mass ejections over the last 3 days up until today. So this is what's been going on the sun. So you can see those ejections there. They're happening. The Earth, the sun is not a sleeping giant. It's one that's certainly awake. And then this one here is a forecast of auroras. So the Aurora Borealis, NOAA at the Space Weather Prediction Center, they put a forecast together every day. You can get it from their website. Just Google Space Weather Prediction Center, and you'll see these forecasts. And this is the forecast for tonight for who's going to see an aurora. And it doesn't look like it's much of a big one, but folks up in Canada, they have a chance to see a mild one. But when the colors change, you can see that it's a much higher chance of seeing it. So all of you aurora chasers out there, I'm sure you probably have that site bookmarked, and it's very, very exciting. We wouldn't have auroras, Lika, correct me if I'm wrong. We wouldn't have auroras if we didn't have emissions from the sun. Is that correct?
Absolutely.
Yeah. So
sun would be truly as boring as astronomers think if that happened. But sun is a magnetic variable star, and it's the magnetic variability that is producing all of these conditions. And that's the difference between terrestrial weather and space weather.
Yeah, and Lika, I would just love for you to tell us real quickly. I mean, I became a meteorologist because I saw lightning when I was 6 years old, and I witnessed ball lightning. It was in my blood, and it was there. It's still there. I get excited every time I look at a cloud. And so, what got you so excited about the sun? What is it that drove you? Was it somebody, some experience, something? What drives you to be so interested in the sun?
Well, very originally it wasn't the sun, it was all stars, and sun is but a star. But then when you go through the process, so I'm an astrophysicist by training. When you go through the process of graduate school, you have to choose a thesis topic. And it seemed like sun is the only star that we can study in such great detail. And I have a story, it's not just a cliche that my life revolves around the sun. My thesis was actually on the solar corona, and there's a lot less we knew back. This is in the 80s, mid to late 80s. I'm talking of 1988 was a total solar eclipse from Philippines that my supervisor, Dick Fisher, with whom I worked for 25 years, actually, took that picture from Philippines. That was part of my thesis. But then there is this first ever suborbital rocket X-ray data collected during the eclipse. So we could actually see what is on the surface, the disk of the sun, when we are seeing the corona in white light, when the moon is blocking it. And, these kind of pictures are dime a dozen today, right? We generate them every second from all our data. But that's the very first picture. And that was actually in Time magazine.
Yeah.
So that was 1988 Saros cycle, 139. Then I went to Libya in 2006 at the invitation of State Department to establish, sort of science diplomacy. That was the 18 years later Saros 139. And in 2024, it's almost 36 years later, is the same Saros cycle coming back. So someone asked the question, right? Are there cycles? Well, trust me, there are cycles.
Let me ask, there's a couple of more questions coming in. Let me ask a first fast one, and then we'll get into some more scientific ones. Where can people get the Eclipse glasses?
So, after 2017, now Eclipse glasses are being sold by lots of commercial vendors. NASA still hands out Eclipse glasses wherever they are. But I would suggest looking up commercial vendors and big stores in your area to find Eclipse glasses.
Okay.
Lika, if I may, I got mine at Home Depot, and I think Lowe's also has it. So, and I was just at Home Depot, 2 days ago, and they still had a little bit left.
And the other point too to make is that you don't have to be in the path of annularity to see the eclipse, right? You can be anywhere in the lower 48, I think even Alaska, right? They'll see it. You can find maps of where the path of annularity is and where partial solar eclipses will be seen. So unfortunately, I'm coming to you from Annapolis in Maryland. The temperature's nice and comfortable, 56 degrees, but we're going to get clouds and rain over the weekend. I'm going to go look for a kite to see if I can fly it. But perhaps there'll be better weather on April 8th. But you can also get online and find a lot of live streaming going on for this eclipse coming, and you'll see probably TV networks covering it as well. So it's going to be exciting no matter what. I just won't be outside. I'll just be looking at a computer monitor to see this eclipse live too.
Actually, let me add to that. NASA has two live stations. One is Corville, Texas. The other is Albuquerque, New Mexico, from where there'll be live projection of the eclipse, and also, more details and talks and things like that.
Yeah, and I just want to end this, and I really appreciate Gideon for not giving us the hook with AMS. Weather Band is a terrific opportunity to connect with so many people around the nation and around the world. But I did just want to leave you with a couple of pictures, whether they're actual pictures or artist renditions. It really does remind us that the sun is in control of our lives in the universe. And when things line up right, it's just amazing what gets captured. And like Lika showed, where we could see from satellite the shadow of the moon on the Earth, they can see it from the space station as well. This is an image in 2012 on May 20th from the International Space Station. This is an image of an annular eclipse taken by the JAXA and NASA spacecraft on January 4th of 2011. This is from Hinode. If you can get out with your family, experience an eclipse, it'll change your life. And really, if you're in the right position, it can really line up. And we hope that this webinar really has given you some excitement and some knowledge. And we also hope that it really energizes the next generation, right? We're hoping that the next generation of explorers are watching this eclipse and watching this webinar and can get out and experience not just the atmosphere, but what's beyond the atmosphere. And I think it will really be a fantastic experience. So
can
I'll
I
just
add one more to that? That's beautifully said, actually, Dave. I think between 2017 and 2024, I think what we might see is what's called the eclipse generation. So there's going to be a generation who grew up with these two eclipses versus the ones that didn't. That's
great. I'll take that 100%. And the one last thing I wanted to share was the number of eclipses coming up. So the next 7 total solar eclipses here, you can see April 8th, 2024, August 12th, 2026 is a total solar eclipse, but look, not over the United States. Got to go to Greenland for that one. The next one, August 2nd in 2027. That's number 3 here. It goes across Northern Africa and down into the Pacific. Down into the Indian Ocean. The next one after that is 2028. Number 4 is over Australia. There's a reason. Get those tickets now. And November 25th, 2030 is number 5, and that is across South Africa and across into Australia once again. So they're going to luck out here. And then on number 6 is 2031, November 14th of 2031. That's number 6. And here it is out over the Pacific. So not really much happening there unless you're in a fishing boat or a cruise ship. And the last one here, 2033 on March 30th. That's number 7. And I think you'll have to join Lika in the Arctic Circle somewhere. That's where that eclipse is going to be. But one final message is, and that is, I wish we could predict the weather as good as we can predict these eclipses because they follow mathematics. So does the atmosphere. But there are all sorts of things that impact the atmosphere. Not as easy as orbital dynamics. So, Lika, I really appreciate you joining us this evening. Thank you so much. This has been a great AMS Weather Band production here. Janine, thank you so much for moderating the questions. And Janine works with Lika all the time, so she's lucky. Send Janine emails. How do I get involved in your job and working with NASA and heliophysics and all that stuff? And Gideon, I'm just going to throw it back to you. We really appreciate you giving us a little extra time. The eclipse waits for no one. So in 3 days, we hope everybody has a joyous experience.
Well, thank you so much. Thank you, Lika. Thank you, Janine. And Dave, thank you so much for taking the time in your evening to share all this with us. This has been fantastic. I am, even though it's going to be cloudy where I'm at, I'm still going to go see what I can see, or maybe find a kite, right? But yeah, with that being said, thank you everybody for joining us today or this evening. And take care. Happy viewing of the solar eclipse if you can. And we'll see you in our next AMS Weatherband webinar. Good night, everybody.
Thank you very much.